Don't forget to subscribe and ring that bell.
Why, hello. It's good to see you again. Yeah, it's me. I'm back. I haven't put up any new videos because I have 9 or 12 series of videos that cover 9 or 12 previous AP Calculus AB exams. And I tell you what, I wanted to do another one this year for a couple of reasons. One, the compliments and the gratitude I have seen on a lot of the comments on those videos is nothing but astounding. Thank you so much. It's why I do this. You know, some of you are saying, thank you for the help. I understand it better now. Some people are like, hey, I was stuck on my homework and now I got it done. Hey, good for you. At least you want to do your homework, right? And a lot of people that would just, say, thank you for your energy. I appreciate it. That's awesome. So I wanted to do another one with 1 week left before the 2024 AP exam. Okay. The second reason I wanted to do this is I was on another site. I was just doing a search for some recent exams, and I saw somewhere that someone had, on a blog or something said that the 2021 free response questions were pretty tough. And it seemed strange they were different from years past. So, bing, 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 light goes off. That's what I want to do in this series of videos. We are going to cover the 2021 AP Calculus AB free response questions. And we're going to start today with free response question number 1. And hey, we get a graphing calculator, which I love. Dig it. Nice. Let's begin. They gave us a table. Love me, tables and charts and graphs. Oh my. So, number 1 says, the density of bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Values for f of r for selected values of r are given in the table above. All right, that was a mouthful. A says, use the data in the table to estimate f prime of 2.25. Then, using correct units, interpret the meaning of your answer in the context of the problem. Okay, I love this. There's no easier way to walk into a part 2 or free response question with a calculator, no less, than something like this. What do I mean? They're asking us for f prime. F prime is the derivative or slope of f at the point 2.25. When I look at my table, I see something. 2.25 would be right here in between 2 and 2.5. Here's the key. You see where it says estimate? It wants an estimate. You cannot find the exact slope at a point because we don't have an equation to take the derivative of. So we're going to estimate it by taking the slope of the 2 closest points to 2.25. And that would be 2 and 2.5. They sandwich 2.25. So I am literally, quite literally, people, going to do, okay, we got y1, y2, x2 is right here, x1, and I'm just going to do change in y over change in x. All right, so we're going to have 10, which is my y2, minus 6, which is my y1, all over x2, which is 2.5, minus x1, which is 2. Now, you can use a calculator, and if you're one of those students that's a little shabby and you want to check everything because you're anal about everything, do it. But we end up with 4 over a half, and if I divide that, I get 8. Now, this answers the first part. We still got to interpret the meaning using correct units. Okay, using correct units. So first of all, let me address the correct units. All right, we had stated earlier that this is a change in y over a change in x. Yeah? Well, what's the label for my y? Or my, it's milligrams per square centimeter. So I'm just going to say this is milligrams per square centimeter. But that should be over my x, or in this case is r, which is centimeters. So my label should be milligrams per centimeter squared per centimeter. That is a mouthful. I feel like I've said that a couple of times now, but don't judge me, kids. Now, let's interpret what this means. Well, since my rate is positive, it's going to be increasing. Yeah, this is a positive 8. So it's going to be increasing. So what I'm going to say is the rate that they give us, because this is a rate, it is a unit per another value, per centimeter, okay? That rate is increasing. So the rate of the rate here is increasing. Or you can say the rate of milligrams per square centimeter is increasing. All right, don't just say milligrams per square centimeter is increasing. It is the rate of it. So, and I think that's exactly how I'm going to start writing it out. The rate, okay, of milligrams per centimeter squared is increasing. You know what? Let's get more specific. Okay, interpret the meaning in the context of this problem. The rate of what? Okay, density of bacteria population. Okay, so I'm going to just change this. Okay, because it says in context. So the rate of the density, okay, of bacteria population in milligrams per centimeter squared is increasing, okay, is increasing at 8 milligrams per centimeter squared per centimeter when they are what? When the R value is 2.25. So when they are distance from the center, okay? When, what's that? The bacteria is, oh my goodness, when the bacteria is right here, 2.25 centimeters from the center of the Petri dish. From the center of the Petri dish. Now, this might be overkill, but it is precise and it is specific and it is in the context of the, and it took a lot longer to write that explanation than it did to actually estimate f prime of 2.25. There you go. And here's what makes this first problem different and what makes kids sweat a little bit. B states the total mass in milligrams of the bacteria in a Petri dish is given by the integral expression 2 pi times the integration from 0 to 4 of r FR dr. Approximate the value of that using a Wright-Riemann sum with the 4 subintervals indicated in the data in the table. Now, here's where my students would crumble. I shouldn't say all of them, but some of them would freak out just a little bit, even the smart ones, because they're like, anytime we do a Wright-Riemann sum, we just have the function here. We don't have times this other variable. It's weird. Here's what I'm going to tell you. Anytime we do a Wright-Riemann sum, or a center, I should call it MRAM, mid, or a left Riemann sum, we never actually do the integration. We look at the values here, and we add them up. We multiply them times the width. Okay? Now, I'm going to do the same thing, but take a look as we set this up. I'm going to set up the first couple. All right? We need to look at our table. First of all, let's start. We are using the 4 subintervals indicated in the table, which means, all right, the first one goes from 0 to 1. So I like to actually make the rectangles. Okay, it's a good visual. The next one after that goes from 1 to 2. Okay, this has a width of 1. The first one also has a width of 1. We'll put our widths up here. Or if you want to call those heights, I call them widths. Potato, potato. From 2 to 2.5, this width is 1. Ooh, it's 0.5. And last but not least, we have from 2.5 to 4. Okay, and that is a distance or width or height of 1.5. So here, I've got to use a right Riemann sum. So for the blue one, okay, the right value that we're adding is 2. 1 is the left, 2 is the right. I got to take that, all right, and I've got to multiply it. Okay, so here we go. Let's start with that. 2 is the right value. I got to multiply it times the width. The width is 1 up here. Okay, so I'm just going to put this times the 1. But notice that takes care of this part. I still got to multiply it times the r. What is the r when f of r is 2? It's 1. So I mean, here's the r's, right? So I'm literally just going to multiply it times the 1. So here's my r. Here's my f of r. And then we always multiply it times the width. Since these widths are different, I'm just going to do each one individually. And there you go. That's the width or the height. And that's all we're adding together. That's it. So don't freak out. Yes, it's slightly different, but no, it's not difficult. Let's take a look at the red one. Okay, the right side of the red rectangle is 6. That width is still 1 up top. And the r value is 2. That's it. All right, well, the next one is green. And we go here. The right one on green is 10. So I'm going to put 10 here. That width is 0.5 or 0.5. And the r value is 2.5. And last but not least, our last rectangle has a right value of 18. That width is 1.5. And the r value is 4. Now, don't forget, this is a lot to set up. But we just set up this integral right here. That's this whole thing. We still have to multiply it times 2 pi on the outside. Oh my goodness. If you make a mistake, it's going to be entering it in the calculator. I almost want to do this without a calculator, but I encourage you to use a calculator to prevent mistakes. All right, so let's turn this on. Up. Turn this on. And if it would turn on, it'd be super sweet. There we go. We're going to start with 2 pi times. Now let's make sure we type this in correctly. It is 1 times 2 times 1 plus 2 times 6 times 1 plus 2.5 times 10 times 0.5. All right. Plus 4 times 18 times 1.5. God, please be correct. And there we go. It is. I did this before on the board here, and I mistyped. I think I put 2 number 1s to start instead of 1, and it was just crazy. But that's our answer. And considering you have a calculator, I mean, goodness gracious, people, 845.088. The calc exam always goes 3 decimal places, so I'm going to leave it 3 decimal places. It doesn't tell me anything about a label. If it was, it'd be milligrams, but don't put it if it doesn't ask you. Okay, so I'm going to be honest with you. 1A was easy. 1B, they had that little tripped up part where they had the X or the R in with the Y or the FR when we did a right Riemann sum. So maybe you're not familiar with that or you hadn't seen that yet, but once I explained it, I hope you got it. So that was the only trip up. And 1C is also really easy, okay? It's just an explanation, and I'm going to draw a little visual to help explain that explanation. All right. 1C reads, is the approximation found in part B an overestimate or an underestimate for the total mass of bacteria in the Petri dish? Explain your reasoning. They are referring to our answer of 845.088. Is that an overestimate or underestimate? Well, the first thing I'm going to tell you is we have a function that is always increasing. So when I graph this, okay, yeah, I could plot the points, whatever, but the points don't matter once they tell us it's always increasing. But for those of you guys that are like, but it's got to go through the points, let's put these 4, or I guess 5 x values on a little graph here. This isn't part of the explanation. This is just 0, 1, 2, 2.5, and 4. Let's go all the way up to 18 at 4. At 2.5, it's 10. Maybe right there, 10. At 2, it's 6. 6, right there. At 1, it's 2. And then at 0, it's 1 right there. So this graph is going to it's going to be constantly increasing, all right, and go up. Now, we use the right Riemann sum. So when I draw these rectangles, the right, from 0 to 1, the right corner is going to touch, and it's going to go over, okay? Then at 2, the right corner is going to touch, it's going to go over. I hope you can start to see this right now. At 2.5, the right corner, and at 4, the right corner. Okay, I only want the area under the curve. I only want this area under the curve in yellow. That's what I'm trying to estimate. Look at all of this space here that's extra, that's in our calculation, okay, that we don't need, that's actually not under the curve. So our estimate is going to be more than what's actually under the curve, so we have an overestimate, okay? So we got to state that and explain our reason. And to me, it's quite simple, all right? First of all, I'm going to state it's an overestimate since we used a right, okay, we used a right Riemann sum, okay, our IE, 2 n's, on an increasing function. Okay, that's just a rule. If the yeah, I was worried about misspelling Riemann. I misspelled function. I left out the N, and kids, don't ever pronounce function without N, please. So if my function was decreasing and I used the right, then it would be an underestimate. So am I using a right Riemann sum or a left Riemann sum on a function that's either increasing or decreasing? If you draw it out like I did here, it's easier to see. You do not need the drawing to answer the question. Okay, you just need the explanation. But sometimes when you write the explanation down, people can't see it. The visualization really helps you see it and get it, and that's the purpose behind this whole thing. All right, 1D. And you know what? If you know what you're doing, this is easy. So I guess the question is, do you know what you're doing? Okay, so 1B is really the only thing that I think could have possibly tripped you up. All right, so 1D states, the density of bacteria in the Petri dish for times, or I should say for centimeters, between 1 and 4 inclusive, is modeled by the function g, which is defined by g of r is 2 minus 16 cosine of 1.57 square root of 3. That's all cubed, cosine on. For what value of k, and k should fall between 1 and 4, is g of k equal to the average value g of r on that interval from 1 to 4. So there's two things that jump out to me that are screaming. All right. If I want to find the average value of G of R of this thing, I want to find the average value. It's not the average rate of change. It's not the mean value theorem. It is the average value, okay, on the interval from 1 to 4. Anytime they ask me for the average value, I need to integrate, okay, from my interval from 1 to 4, G of R, dr. But if it's average, I multiply that by 1 over the difference in the bounds. Okay, and that's what I'm going to start with right here. Okay, let me move this over here. Oh, you poopsicle. Let's move this right over here. No, 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 right there. How about that? Boom, we'll take it. And now I want to take this so you guys can see this. Turn this on. On. And I will clear that out. And we're going to take alpha y equals enter. 1 over, I'm going to type everything in as I need to. Go math 9 from 1 to 4. Now of my G of R equation, 2 minus 16 cosine. Ooh, I should put that in parentheses. Parenthesis, cosine of 1.57 times the square root. We are using x instead of r. Close that. Let's pop out and close it. And then we got to cube that thing from cosine on dx. Okay, that was a lot to type in. But it's typed in, it's great. We got this great little thing here. Let's hit enter. And we get 9.87579, let's call it. Okay. We get, this is approximately 9.87579. So what are they saying should be equal to this? G of k. Like there's some number between 1 and 4 that if I put it into this equation, okay, this is going to equal G of some number that I put in here. So they're saying, what's this number? So that's like, you can still graph G of R. They're just replacing R with another variable K, which happens to be between 1 and 4. So I'm going to graph this without integrating it and see where it crosses this number. Because I want to see where my equation, 2 minus 16 cosine of 1.57 square root of R cubed, just from cosine is cubed. I want to see where this equals this. Just graph them both and see where they intersect. And the beautiful part is you only got to check between 1 and 4 on the x-axis. That's exactly what we're going to do. All right? Here we go. So I'm going to go to y equals. And I'm going to put my, well, first of all, if you got a different number than I did for the first part, you better make sure your mode is in radian. Okay, anytime we deal with trigonometry and calculus, radian. Okay? So I've got 2 minus 16, parenthesis, cosine, 1.57 times the square root of x, close it, cube it. Fantastic. And that's got to be equal to that first number that we came with, the integral, 9.87579. All right, so when I do this, my window, I only care from 1 to 4 on the x-axis. I don't care about negative. I got to make sure I see at least 9.87, whatever, on the y. So let's start at 0 and go up to 12. Let's graph that. Okay, here it is in all of its glory. Here's our G of R equation. And here comes 9.875 right there. So I want this intersection point right here. I'm going to look to see where this intersects. And God bless us for using the calculator. Second trace intersect. And I enter 3 times. 1, 2, 3. If I look at the bottom, it is 2.47497. Now, on my test, I like to draw the sketch. I like to sketch everything out. Just if I have the time, I just like to sketch things out. And I do and I do this. I do something that looks like this. And this is G of R. We're going to have like 1, 2, 3, 4. And here is the line right there. This is 9.875. That's a 5. It's a very bad 5. But I know now they intersect right here, which is at x is approximately 2.497. Okay? So they want to know what's the value of k. So you say k is approximately 2.497. All right. So that wasn't horrible. We got through it. We're good. We're smart. We're awesome. We're awesome. The only thing that maybe you get tripped up on was part B. You didn't know that RFR thing. But guess what? You know it now. No excuses now. And maybe this one, you had to see it set up, because I know sometimes the words or whatever. But once you get the setup, especially in problems where you get to use a calculator, man, the rest is cake, my friends, cake. And if you've watched any videos, you know I love cake, and I love chocolate cake. Send it to me at P.O. Box. No, I'm just kidding. I don't want any food in the mail. I will see you guys later for free response question number 2. See ya.
Don't forget to subscribe and ring that bell.